Hello students, in this lecture we'll take few examples of first order systems. Now these examples are some physical examples. Now the very first example which we'll take in this system in this lecture is of liquid level. Liquid level tank. Now in this, let's consider a tank. There's an input to this tank and then we have an output of this tank. Now at the output we have a valve which provides a flow resistance. The liquid in the tank is having a height h, which is a function of time. The input flow rate is Qt, the output flow rate is Q naught T, and the density of the fluid is rho, which do not changes, and the cross sectional area of the tank is A. Now such type of systems are of two types. One is linear systems and the other one is non-linear systems. Linear and non-linear systems. Now linear systems are those systems where the outlet flow rate is represented by this expression, that is the head and the outlet flow rate are having this relation, that is directly proportional. So these type of linear systems are only possible if the flow is laminar in nature, laminar flow. Now for non-linear systems, the outlet flow rate in the head, it varies with this correlation, that is C under root of H. Clear? Now these are possible in the case of turbulent flows. Clear? So we'll be starting both linear and non-linear systems, that is for laminar system and for turbulent systems. Clear? Now the very first example which you're going to take is liquid level tank for the linear system, that is for laminar flow, that is the outlet flow rate varies with this relation with respect to the head. And the second case we'll take is a non-linear system where the outlet flow rate varies with the head by this expression, that is C under root of H. That is a non-linear system. Now for first, that is linear system, what we do is we apply the mass balance on this tank. We'll write the mass balance on this tank. Now mass balance is mass flow in minus mass flow out is equal to rate of accumulation of mass within the tank. Clear? Now mass flow out, mass flow in is density into the volumetric flow rate, that is Q, out density into Q naught, and accumulation of mass within the system, that is density into d by dt of A into H, that is the volume, rate of change of volume. Clear? Now density of the fluid remains same, inlet, outlet, and within the tank, so it gets cancelled up. So what we are left with is Q minus Q naught is A dH by dt. Since A cross sectional area is constant, it can be taken out. Now Q naught in case of linear is represented by H by R. So substituting back over in this equation, so what we have is Q minus H by R is A dH by dt. Now upon rearranging, what we have is AR dH by dt plus H equal to R times Q. Now you see, this is a perfect example of first order system where this is your tau and this is your resistance Kp, sorry, your gain Kp. Clear? Now You can directly write the transfer function over here, or let's derive the transfer function for this thing. Now we know that it is, for the first, it's q minus q naught is a dh by dt, or we can also write q minus h by r as a dh by dt. Now under steady state, it will be qs minus hs by r equal to 0. So 1 2, so we can have 1 minus 2, so what do we have is q minus qs minus h minus hs by r equal to a d h minus hs by dt. Now q minus qs can be replaced by capital Q, h minus hs can be replaced by capital H, equal to a dh by dt, which upon rearranging can be written as ar dh by dt plus h equal to r times q. Clear? It was something, it's similar to what we have written over here. Clear? But now it's in the form of a deviation variables. Now taking the Laplace, considering the initial conditions to be 0, so this comes out to be tau s into hs plus hs equal to r qs. So hs by qs can be written as r upon tau s plus 1, where tau is nothing but area into the resistance. So this is the transfer function of the liquid level tank. It's a first order system. Clear? Now further, now this, what does this give? This basically give us the variation in the head, with respect to the inlet. So if the inlet changes, how does the head, the liquid level in the tank changes? Clear? So that is represented by this, that is h by q. Now if you divide by r on both the sides, so we have hs by qs equal to r upon tau s plus 1. So if we divide r by both sides, so what we have is, so we'll have 1 over here and we have r over. Now what is hs by r? That is q naught s by qa. So that is 1 upon tau s plus 1. So this is how the outlet varies with respect to inlet. This was how the head varies with the outlet, with the inlet, sorry, and this is how the outlet varies with the head. So you can see in both the cases it comes out to be the again first order, which is 1 upon tau s plus 1. Now we know if the inlet, that is qs, varies sinusoidally, varies step, or varies impulse, so how does the head or the outlet varies? Now if suppose if qt varies step function with aut, so what will be qs? Qs comes out to be a by s. So in that case what will be ht? ht will come out to be ar into 1 minus e minus t by tau. That is what we derived in the previous lecture. For any step input, how does the first order behave? So it behaves in this way. Clear? That means if this is the input, this is the liquid level. Now suppose if you suddenly increase the input from 5 feet cube flow rate to 10 feet cube flow rate, so there is a step input of 5. So how does the liquid level, this liquid level will change? Obviously if you increase the inlet, the liquid level will increase, so that increase will be presented by this expression. Clear? Further, now suppose if the inlet varies suddenly, that is delta t, that is in this ongoing process from somewhere you added directly 10 feet cube of liquid, suddenly what will happen? The level will increase, and with the passage of time, what will happen? The liquid level will decrease. That is what the impulse function is. So we'll see. Now for impulse, we know that qt is delta t. So what will be qs, q naught s, basically qs. Qs will be 1. So your hs by qs was r upon tau s plus 1. If qs is 1, so hs becomes r by tau over s plus 1 by tau. So ht becomes r by tau e minus t by tau, and tau is ar, so 1 upon a into e minus t by tau. So you see, if you suddenly increase the level, this is the ht, this is time. Initially the level is very high, and then with the passage of time it decreases, and that decrease is represented by this exponential e minus t by tau. Further, now suppose if the qs qt vary sinusoidally, that is a sin omega t, so your ht will be again represented by this term a square tau square omega square plus sine of omega t plus 1. So this is what we have already derived in the previous lecture also. So you can clearly see, if the input is sinusoidal, the output will also be sinusoidal, but the only variation is the output will have the amplitude lesser than the input amplitude, and the output will have the lag, and that lag is represented by this phase angle, which is tan inverse minus tau omega, or you can also write it as minus tan inverse tau omega. Clear? So if the input is this, the liquid level will vary in this direction, and this will be your lag, that is phi. Clear? So this is what it was for your linear systems. Now let's take example of a non-linear system. Now in the non-linear system, the input and the output is there as it is. There is a head, there is a cross-sectional area A, input is T, there we have a resistance, and the output qt. But now the output is varying in this ratio with the head. Clear? Now in this we'll write the balance, that is q minus q naught is a dh by dt. We substitute the value of q naught, which is c under root of h, becomes a dh by dt. Now this is a non-linear system, and Laplace do not solve, and Laplace is not applicable in non-linear systems. Laplace is not applicable. So how do we solve this equation? Now for this equation, in order to solve this equation, what we're gonna do is we're gonna linearize our non-linear system. We're gonna linearize our non-linear system. How? Now using Taylor series. So this is the case of linearization of a non-linear system. Now what does Taylor series says? Taylor series says, suppose you have a function which can be written as f at a, that is x is equal to a, plus f dash a into x minus a, plus f double dash a x minus a whole square by 2 factorial, and so on. So if you have q, now a non-linear system is q naught, which is a function of h. So this can be written as q naught at steady state, that is hs, plus q dash naught at steady state, into h minus hs plus higher order. Now let's neglect the higher order because h minus hs is very much less than 1, so we can neglect the higher order systems. So what we have is, we have a simple system, that is q naught at h is q naught evaluated at steady state plus q dash naught at hs into h minus hs. Now what is this? We know that q naught is c under root of h. What will be q dash naught? That will be half c h minus half. And then what will be q dash naught at hs? It will be half c hs raised to power minus half. Clear? So we substitute this value of q naught directly over here. So upon substituting, so what do we have upon substituting? So we have q naught equal to q naught at steady state plus half c hs minus half into h minus hs. Now this is somewhat equal to y equal to mx plus c, where this is c and this is your mx plus c. So this term is the slope. So that is, if this was q equal to c under root of h, we have linearized it. Sorry, let me plot it again. So we have linearized it using this equation, which has a slope of 1 by 2 c hs raised to power minus half. Now in the case of linear systems, that is over here, the slope was 1 by r. So again in our case we'll take the slope as 1 by r. So 1 by r is equal to half, let's say 1 by r1, 1 by r1 as 1 by 2 c hs raised to power minus half. So what will be r1? r1 is nothing but 2 under root of hs plus c. So this equation approximately becomes q naught s plus h minus hs by r1. Clear? And now q naught, we know that is q naught s plus h minus hs by s. Now this q naught s is nothing but qs, because initially if the inlet and the outlet are same, so q naught s is nothing but qs. So substituting this value of q naught in this equation, that is over here in this main equation. So substituting b in a, substituting the value of q naught, that is this, in equation a. So what do we have? We'll have q minus q naught as a dh by dt, and q naught is nothing but qs plus h minus hs by r1. So upon substituting we have q minus qs minus h minus hs by r1 equal to a dh by dt, or can I write dh as dh minus hs, because obviously dhs of by dt is 0. So a dh by dt or a dh h minus hs by dt is same. And what are these things? These are deviation variables. So capital Q minus capital H upon r1 a dh by dt again comes out to be first order. Take the Laplace, so we have hs by qs over r1 over tau s plus 1, where tau is a r1. Now it's again comes out to be the same. The only difference is over here in a linear system it was r over tau s plus 1, whereas in a non-linear system it is r1 over tau s plus 1, where r1 is your 2 under root of hs by c. That means first we need to evaluate r1 under steady state conditions, and then we can use that r1 directly over here to calculate the transfer function for your non-linear system. So again, whether it's a linear system or non-linear system, for liquid level tank of first order, the transfer function is always this thing, that is r upon tau s plus 1. Clear? Now the second example of a physical example is mixing. Mixing process. The first example was the linear tank, and in that we discussed upon non-linear and linear systems. The third example is your mixing process. Now in this, let's consider a mixing process. We have an input stream and we have an output stream, and there is a stirrer. It's a well stirred process. That's the input Q and that's the output Q. In the input stream, let's say X is the concentration of the salt, and in the output, let's say YT is the concentration of the salt in the output stream. It's a constant hold up, so volume V is constant in the tank, and the concentration of the salt in the tank is Y. Now further, the salt concentration at the input is a variable, it's changing. So if X changes, obviously the concentration of the salt at the outlet will also be affected by it. So let's find out how the salt concentration at the outlet varies with the salt concentration at the inlet. So for this, let's assume that the density of the fluid is constant, or the density of the solution is constant. Clear? So we'll apply the mass balance, that is flow of salt in minus flow of salt out is equal to rate of accumulation of salt in the tank. Clear? So input salt Q into X, output Q into Y, and rate of change of that will be V into Y, where Q represents the inlet volumetric flow rate and Q, it's at inlet and outlet volumetric flow rate is same, that is Q. So now at steady state, Qxs minus Qys is 0, subtracting each other. So we have Qx minus Xs minus Y minus Ys equal to, volume is constant, so dy by dt and Y minus Ys. So this becomes I'll write again, Q into X minus Xs minus Y minus Ys equal to V dy dt of Y minus Ys. So deviation variables, X minus Xs is capital X, Y minus Ys is capital Y. So Q into X minus Y is equal to V dy by dt. So again first order, let's rearrange. So this becomes V by Q dy by dt plus Y equal to x. First order, take the Laplace, so we have ys upon xs is nothing but 1 upon tau s plus 1. So that means where tau is nothing but v by q. So again, first order, so if the concentration of the salt changes by step, if the salt concentration changes by impulse, or if the salt concentration changes by sinusoidally, we know the responses. Clear? Now you can clearly see the first order, the transfer function remains same, that is 1 upon tau s plus 1. The only difference is the time constant definition is different. For thermometer it was mc by ha. For liquid level tank it's a into r, or a into r1 in case of non-linear tank systems, and for mixing systems time constant is v by q. Clear? But the overall transfer function of the first order remains the same, that is 1 upon tau s plus 1. Clear? So these were the few examples of the first order system. So in the next lecture we'll be taking few numericals related to thermometer and for liquid level systems. Now in this lecture, if you have any problem, you are most welcome to discuss. My email ID is given on the very first slide, that is parminder.singh@thapar.edu. Thank you so much.